All right, so here are the video notes for week 9 notes. Unit test, October 31st. This could be what, if you were in my Tuesday, Thursday class, we started these notes as 8B, but we didn't finish them. So I just moved everything to week 9 with the rest of the notes that we're going to do this week. All right, so here, these are the intermolecular forces. Now, most likely you know by now dispersion is the weakest, then dipole, then hydrogen bonding, and then lastly, ion dipole is the strongest. So this is going from weak to strong. However, if we look at the right, there seems to be a limit of how high hydrogen bonding, the strength in hydrogen bonding. But there isn't a limit in dispersion or dipole. Hence, if a compound has similar dispersion forces, it's going to go in this order, like similar molar masses. But if a compound has a ton of dispersion forces, it can have a higher melting point or boiling point than something with hydrogen bonding. And I'm going to ease you into that, to what the data analysis for that. So it really is just data analysis for that. So let's look at that. So the next 2 slides are somewhat of a review from week 8. Now pull out your periodic table, and these are all the noble gases, so group 18 or group 8A. And notice how as we go down, the radius of the atom increases like periodic trends do. The molar mass increases and the boiling point increases. And this is because when the radius increases, dispersion increase, and when molar mass increases, dispersion increases as well. So looking at the periodic table right now, we're going down. We're not going to the left or right. We're just going down the periodic table. The amount of protons, or the top number, in that element are increasing. The molar mass, the bottom number, are increasing as well. And we can see on the far right of this visual that the boiling point is increasing. The reason why the boiling point is increasing is because as we go down the periodic table, there are more electrons, the radius is larger, and the dispersion forces increase. Hence, there's more chance that electrons are going to be in a polar position to be attracted to the protons of the other compound. So if that didn't make sense, replay that because it's an important concept. This is saying the same thing. All of these compounds right now, you might have heard maybe in talking about gasoline or something, but you don't know what they are and you don't need to know what they are. But yet, they are all nonpolar, meaning they're just large carbon chains. And we see that carbon chains, meaning carbon, 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 carbon with just hydrogens all around it, very symmetrical, nonpolar. We see though, as the molar mass increases, the boiling point increases, and somewhat exponentially. or not exponentially, in a straight line. And that again is because with a higher molar mass comes more electrons, comes more dispersion forces. Now, a question that I would ask from this would be something like, well, we know water has 100 degrees Celsius boiling point. But look at how heptane also has 100 degrees Celsius boiling point. Heptane is C7H16. Pretend there's hydrogens around those, or not, it doesn't even matter. We know it's symmetrical, we know it's nonpolar. Water, so heptane on the right just has dispersion. Water on the left has dispersion, dipole, and H bonds. So how could heptane have the same boiling point as water? And what it comes down to is heptane, its dispersion forces are as strong as the dipole. So these are equally as strong as the dispersion, dipole, and H bonds in water. And that's true. Heptane is in a lot of gasolines and so forth. It is a liquid at room temperature despite being completely nonpolar, but it's a huge molecule. So molar mass of 100 compared to molar mass of 18 of water. Yet they have the same boiling point. Hence, dispersion forces can make the intermolecular forces between two compounds greater or equal to something that just has hydrogen bonds, or to something that has all of the different dispersion forces. All right, so now let's look at another example. Fluorine, so look at your periodic table. Fluorine is a halogen, group 17. They are diatomic. So fluorine, as you go down a periodic table, the radius gets larger. And evidence that this boiling point and melting point thing, and keep in mind, when boiling point goes up, melting point goes up. Evidence of this is, well, fluorine at room temperature is a gas. Chlorine is also a gas, but bromine is a liquid. And we did work with bromine once, and iodine is a solid. So, since iodine has the most protons, has the largest radius, therefore the most electrons, the dispersion forces are so great that it makes the melting point greater than room temperature. For bromine, that would be the melting point. So we'll make the boiling point greater than room temperature. So as you go down the periodic table, the radius increases. So again, here's another reminder to make sure you know the trend for radius. If you don't know that, you are in trouble. Yet, if the masses are equal, meaning dispersion forces about equal, so I don't know how to do about, something like that, I think. Then the one that is dipole is going to have a higher boiling point or melting point. Hence, ethane is a nonpolar compound. but it has a lower boiling point and melting point than formaldehyde, because formaldehyde is polar. It has dipole bonds. It does not have hydrogen bonds because those hydrogens are connected to a carbon. If we're to draw these, if we're to say which one has the highest boiling point, the 1 that is dipole is going to have the highest boiling point. This is going to be highest. The rest of these are nonpolar. And we can then assume or make at least a hypothesis, or at least get the question right, that the highest is going to be this, the lowest is going to be the one with the least amount of dispersion forces, which is going to have the lowest molar mass. CO2 has a molar mass of 44 grams per mole, and CH4 has a molar mass of 16 grams per mole. So this is going to be the lowest. Now keep in mind, if the masses are somewhat similar, or it's not an extreme difference, you can assume the one with hydrogen bonds is going to have also a higher, like here, HF, HCl. This is a good example for what else could be asked on this is, well, which one has a hydrogen bond? Or I'm sorry, both of these have dispersion. Both of these have dipole, but only HF has H bonds. So HF, because it contains hydrogen and Fun, is going to have a higher boiling point and melting point. Why is that? Fluorine is stronger than chlorine at pulling those electrons over. We have a bigger negative and bigger positive for the HF. Electrons are negative. Remember, those electrons are in the middle. Those electrons are being pulled over. And if you have a stronger magnet, it is harder to pull these HFs away from each other to evaporate it. So here we have methanol. That's going to have the highest boiling point. N2 is going to be nonpolar, so that's going to have the lowest melting point. And then CO just has dipole. So like the highest, some teachers teach us where they go list the most important intermolecular force. So like Dr. Nickel, who teaches the nursing students, you know, I was teaching them, okay, list dispersion, dipole. And they go, no, you can't. You don't get extra point if you just write dispersion. That's been made clear. Because all she wants is the strongest of them. So CO is dipole. I want all of them, but CH3COH has H bonds, but you'll see what I mean. And N2 just has dispersion. So you know that, and all these molar masses are going to be somewhat similar. They're not going to be hugely different. So N2 is going to have the lowest boiling point or lowest melting point, and CH3OH or methanol is going to have the highest because it's hydrogen bonding. Now, it's going to be critical here that you analyze this graph because it's something that I'm going to use. So we did this in class, but I'm going to do it again here. First thing I'm going to do is cross off all of the polar compounds. So, well, let's look at what the graph says first of all. We have the formula, the name, the molar mass, and the boiling point. And usually, if it was based just on dispersion charges, as molar mass went up, boiling point should go up. But obviously, we see here, it doesn't. And that's because these either have hydrogen bonds or they don't. Or so either they have H bonds or just dispersion. So I'm gonna do what I did in class, but if what I say doesn't make sense or I think it's best to look at this and just analyze it and understand it in the end. I'm going to cross off all the ones that have hydrogen bonds. And those are the ones with the OHs on it. So when you see an OH on something, and you might, if you take biology or A, you know it's going to be polar, it's going to dissolve in water. B, you know it is going to have a high melting point and a high boiling point relative to other molecules its size. Anyways, we have methane, ethane, propane, butane. We see as molar mass, these are all nonpolar compounds. So right now they're just dispersion. We see molar mass goes up, as does the boiling point. So 16 to 30, so it looks like it goes up, 14 every time. And the molar mass and boiling point goes up somewhat of a relative amount each time as well. But all right, so then here, now if I cross off all the nonpolar compounds, and I just have the ones with hydrogen bonds, and I'm going to ignore water for now, we see that as molar mass increases, so does boiling point. Now, the reason for that is, again, dispersion forces are increasing. So even though it has hydrogen bonds, the reason why the molar mass is increasing, or the reason why the boiling point is increasing, is because the molar mass is going up, which means there's more dispersion forces. Yet, if we're to compare two with a similar molar mass, like let's say ethane and methanol, 30 and 32, you couldn't assume that the boiling point is going to be about the same. Methanol has a much higher one than ethane because it has hydrogen bonds. So it's almost like that initial amount is greater for things that have hydrogen bonds or dipole. So analyzing this graph and fully understanding this graph and where it's coming from is important. So it's a graph that I've used many times, and a graph that I have asked students to just, whether or not my explanation makes any sense, if you look at it and just notice the OHs, notice the molar masses, notice the boiling point, you can correlate what is being asked. There is one outlier here, and that is water. So water is 100. All of these start low, get higher. So both for polar and nonpolar. Now, but water has the highest of all of them. Hence, both water and 1-propanol have dispersion, dipole, and hydrogen bonds. Yet they have the same, and I guess we could say, 97 to 100. We can't say it's the same, but we could, let's just say it's the same, and that's fine. They have the same boiling point, despite the fact water's molar mass is so much less. They have the same intermolecular forces, but water's boiling point is the same as 1-propanol. And that is because of something that we've learned earlier, the special properties of the amount of hydrogen bonds that water can form and the amount of hydrogen bonds per size water is. So again, water is very unique. So it's like almost like, well, water is starting off with double the hydrogen bonds. But generally speaking, they should be similar No, never mind. I should take that back. Generally speaking, this one should be higher. If it was any other polar compound with hydrogen bonds other than water, the one with the high molar mass would be higher because it has more dispersion forces. So spend some time on that. This slide is somewhat redundant. I copy pasted some slides from last year because I thought last year's lesson went really good, so I just pasted some in, and so it's sort of redundant. But as intermolecular forces, so does boiling point and melting point. Dispersion's usually less than dipole, usually less than hydrogen bond. But why usually? I mean, that's something that we talked about quite a bit, and I'm just going to show you an example. So these, again, are the non-polar carbon structures. They're not, usually they're not in a straight line. Like if we made those, those little things I brought in for you to build, I don't know, I'm trying to figure it out, but it would go more like that, but still, these are symmetrical. These only have non-polar charges at the top, but look at how boiling point goes up. And then we have hexane again here. Then we have hexanone with something called a ketone there, so it ends in -one as organic chem, but that is then polar. But look at how all the hydrogens are connected to a carbon. So hexane just has dispersion. Hexanone has dipole. And then we have hexanol with an OH, and that hydrogen is not connected to a carbon. So that does have H bonds. And the boiling point goes up. I would expect to go up a little bit more, but I don't know, it's fine. But then we can look at octane, which is a symmetrical compound, and it has a boiling point between those two. Hence, the dispersion forces, and this might be tricky, but it's good if you follow this. The dispersion forces of octane are greater than the dispersion dipole forces of hexanone, but less than the dispersion dipole and hydrogen bonds of hexanol. So, believe it or not, what I said does make sense. So play back if it didn't, but that is important, and we see that through boiling point. All right, so here is just, I want to visually show you what salts are. So I've been saying this here and there throughout the semester, that a salt is essentially between a cation, positive charge, and an anion. They call them salts. You hear salt, you think NaCl. But these are all salts. Look at how we have potassium sulfate there, ammonium sulfate, sodium chloride. So that's the one that you think, sodium chloride. They all look the same. So that's why they're called salts. Between a cation and an anion, that all dissolve. And we're going to do some practice ones, and I'm going to give you some demonstrations on these as well to show you. So not all dissolve. For example, NaCl does dissolve. So you know if you put NaCl in water, it breaks down to Na plus, Aq, and Cl minus Aq. However, you did a lab some weeks ago where you put magnesium oxide in and nothing dissolved. So like no reaction occurred. Like you put it in, it ended up being like a colloid, and so it didn't dissolve. And some salts do dissolve and some salts do not. And that's what the new lesson is on. So you'll be given this table. These are the solubility rules, meaning like if we took a salt, if we tried to put it in water, would it dissolve? would it be soluble? Would it dissociate? So let's say, I'll just pick one. Let's say if it's Na2 SO4, so sodium sulfate. I can look for Na. There's right there. And it says compounds containing the following ions are generally soluble. Na is right there. And it says exceptions, none. And all you have to do is find one of them. But it also mentions sulfate right there. It's soluble, exceptions, when it's paired with strontium, barium, lead, silver, calcium. It's then insoluble. So students do pretty well reading these rules, but it takes some practice. So again, if I said, how about if I said MgOH2? I don't see Mg anywhere, so I'm looking for OH2. It says compounds of the following are generally insoluble. So chances are this MgOH2 is insoluble, except when paired with lithium, sodium, potassium, or ammonium. So this is insoluble. So with enough practice, you are able to read this table well. I'll give you the ALEKS table as well. I think the ALEKS table is better. I just don't have it with me, or I didn't have it when I was making the notes. I didn't know where to find it, and I had to get these notes done. So I am going to skip the ALEKS and stuff because those you can always practice. Ag is a +1, NO3 is a -1, K is a +1, Cl- minus and -1. So you definitely want to do some of those ALEKS, and you'll have the notes before you get here anyway. So the positive goes with the negative, so it forms AgCl. And KNO3. And we want to know if a solid forms. So we're going to the solubility rules. I'm looking at chlorine. It says chlorine compounds are generally soluble except when it's paired with Ag, Hg2+2+, or Pb. Therefore, this is a solid. And KNO3, group 1 elements are always soluble. So this is an AQ. Therefore, a precipitate does form. You're then going to be asked to write the net ionic equation. All you have to do is take the solid of the precipitate that forms and work backwards. Now, ALEKS explains it differently, and you can do it that way as well. But the only thing that matters are the things that actually react. And that's the net ionic equation. It then asks, what are the spectator ions? Meaning, if this is aqueous on this side, nothing happens. Meaning, something dissolved on both sides, it doesn't bond with anything. So the spectator ions are K plus and NO3 minus. Because that is still aqueous, since it's aqueous, we know that the dissociation reaction is that. And so I have that answer right here, the net ionic equation. See the solid, and then if you want to do it how this is essentially how everyone does it, you can cross off stuff on both sides and find then the net ionic equation. I don't think you have to do all that though. Like here, that's aqueous. Those are the spectator ions. This is the solid. Work backwards for the net ionic. And I'll show you another one here. So magnesium is a 2+, nitrate is a 1-. Sodium is a +1, carbonate is a 2-. So you'll always be given the polyatomics. Positive goes with negative. So the product is going to be MgCO3 and NaNO3. I'm going to look at the sheet. I'll give you a hint. Whenever something is group 1 element, like sodium, potassium, or if it's nitrate, it's always soluble. So I don't check that. This is going to be AQ. I automatically know those are the spectator ions. So spectator ions, because that's going to be aqueous. Now MgCO3, we have to check. We can look at the solubility rules. It says CO3 compounds containing the following ions are generally insoluble except when they're paired with lithium, sodium, potassium, or ammonium. So therefore, this is a solid. So the double replacement reaction forms one solid and one aqueous. Thus, this reaction, the net ionic reaction here, is Mg2 plus. So again, I'm going to say, just based on my experience, what is have students work backwards. Net ionic equation. Just write what forms as a solid and write the ions of that substance. And this is net ionic equation. Spectator ions right there. And I have the key right here. So forth. All right, so SR, Br2. So the positive, SR is a 2 plus, Br is a minus 1, potassium is a plus 1, SO4 is a 2 minus. Positive goes with the minus, so that's going to be SR, SO4. Positive is going to go with the minus, it's going to be plus K, Br. If I look at the solubility rules, this is aqueous. If I look at strontium sulfate, look at sulfates. It says sulfates are generally soluble except with strontium, barium, lead, silver, calcium. Therefore, this is a solid. So I'm going to ask you to write two things. What is the net ionic equation? I'm starting with the solid, and I'm just working backwards. So again, you're going to see on Alex, you're going to see on the practice problems, or they write it all out, and then they cancel out both sides. You can do that too. I'm just going to write whatever the charges it makes it into. Then what are the spectator ions? Meaning, what's aqueous in front of it on both sides? Well, it's the only thing on the right, on the product side, that's aqueous. So spectator is K plus and Br minus. And there we see the answer. Now, it almost seems like all the ones that we're getting are solids. However, if it forms a gas, solid, or liquid, it forms a reaction. Now, when something starts with hydrogen, it is an acid. If something ends with NaOH or ends with OH, it's a base. Hydrogen's a plus 1, chlorine's a minus 1, sodium's a plus 1, hydroxide's a minus 1. We're going to do a double replacement. First with second, NaCl, AQ, and HOH, liquid, hence H2O, liquid. So HOH is just another way of saying water. So if you get a acid, hydrochloric acid, and sodium hydroxide, NaOH, you make it a liquid. And so I'll make a deal that there won't be any gases on it, but you'll probably get one like this. And we can rewrite that equation. So I'm going to rewrite that right here. HClAq plus NaOH AQ H plus, Cl minus, Na plus, OH minus, plus goes with minus, plus goes with minus, then the plus is always first, NaCl, AQ. So since that's AQ, we automatically know spectator. Na plus and Cl minus. And the net ionic equation, so that also forms H2O liquid, because H plus and OH minus forms H2O. So the net ionic equation for this would be this. So above here in the link, I have just a bunch of these. I would, though, think that it's better to practice the ALEKS ones and to make sure the ones that I did make sense, because ones up here can, I mean, it's just the same thing over and over again. If you see the pattern in just a couple, you're good, really. But you have to see that pattern. So maybe practicing more is good. All right, last question on your test is going to be balancing simple equations. And this is the verbiage I'm going to use. Balancing simple ones are not that tough. So if you practice some, or if you're able to get the ones that I have on here, you'll get the rest. So here's a good example of the steps. We have Br, two diatomics. We need some numbers in front to balance. Now, if we went down the rules, balance hydrogen, but balance everything but hydrogen and oxygen first. So let's say we balance iodine here, and I put a 2 there. Then that is 2, and then bromine would be 3, and this would be balanced. Let's check it out. 3 times 2 is 6. 1 times 2 is 2. 2 times 1 is 2. 2 times 3 is 6. The other way that I think would be good to look at this is to see that 3 right down there, and then the 2 is on the other side. Right when I saw this, I thought, okay, well, I'm going to put a 2 in front of the IBR3, and that's going to be the right answer. And it ends up being the right answer, but I'm just showing you can solve multiple ways, or if something doesn't work, try the other way, and it will work. So because you can't really put, or you can't put a 2 into a 3, let's just put a 2 there. Therefore, it makes bromine 6s. Therefore, we can put a 3 there and a 1 there. And so either way for the first one would work. 2 in front of the most complicated one, hence where there's a 3 subscript and there's 2 subscripts on the other side, or balance the non-hydrogen oxygens first. The trouble that you would come in with this, though, is if you tried to balance the bromine, if you looked at the bromine first, and that sort of would make sense because bromine's the first here, you saw that 3 there. And, you know, at that moment, I want you to think, okay, well, let's just put a 2 there. And it's going to work out, which it does. So this is somewhat similar to the last one, but let's just follow the normal rules and see how they work. So we have nitrogen plus hydrogen forms ammonia. So diatomics forms ammonia. Balance everything but hydrogen and oxygen first. So I can balance nitrogen by going there. So now I have nitrogen on the reactant side 2, nitrogen on the product side 2. On the product side I have hydrogen 6. So I got to put a number there to make that 6. I'll put a 3, hydrogen 6. Now you can also keep in mind, like these are easier where, if you solve them, you solve them. You see the 2 2s there, you see a 3 there. You know that if a 2 can't go into 3, so you can put a 2 in front of the most complicated 1, hence 1 and 3, and you'll get the same answer. All right, so here we go. Balance everything but hydrogen and oxygen first. So that's going to be a 4 because we need 4 phosphoruses on both sides. Now we have to balance hydrogens. 4 times 3 is 12. That's 12. So what? I got to put 1, 3, 6 here. H, 12. So 6, 1, 4. And it balances out. Balance everything but hydrogens and oxygens first. So I want to balance the sodium first, put a 2 there. Then I want to balance hydrogens, or no hydrogens. Then I want to balance oxygens, and oxygens are balanced. Sodium's 2, oxygen's 2, sodium's 2, oxygen's 2. Keep in mind 2Na means the same thing as Na2. There's 2 for both of those. Balance everything but hydrogen and oxygens first. We want to balance the carbons. Then balance hydrogens. We want to balance the hydrogens. 3, 1. Carbon 2, hydrogen 6, carbon 2, hydrogen 6. So there's a 2 there. I put a 2 in front of carbon. I knew carbon was then balanced. And then want to balance hydrogens. There's a 6 there, so I put a 3 there. So maybe take it slower this time. All right, so V2, 3. So here, I want to balance the hydrogens and oxygens first. So I'm just going to go through the thought process that students will go through. So if I put a 2 there, I now balance irons. Fe is iron. I now want to balance hydrogens and then oxygens. There are no hydrogens. Oxygens, I can't really balance that. I could put a 1.5 there, and that would be right. You would then have to multiply everything by 2, but we'll do that in a later lesson. Hence, what you should do if it just doesn't run smoothly like that is put a 2 in front of the complicated one. Then start over. If we put a 2 in front of Fe, we then can put a 4 there because there's 4 Fe's on the reactant side. 2 times 2 is 4. 2 times 3 is 6. Now irons are balanced. So we have to put a number there to make oxygen 6. And that would be a 3. 3 times 2 is 6. So those are balanced. Hence, when in trouble, put a 2 in front of the most complicated one. And really for these easy ones, if you got like a 3 there, you know you're going to have to put a 2 in front of it. Because if there's no 3 on the other side, you need the least common denominator or whatever it is. I don't know. This is the same one. Might be. I don't know. So Fe2O3 forms Fe plus blank O2. All right. Yeah, it's the same one. Again, I'm thinking this. I'm putting a 2 there to balance the non-hydrogen oxygens. And I go, oh gosh, I got to balance that oxygen. So forget this. and I'm just going to put a 2 in front of the most complicated one. And it's the same one as the last one. All right, so what I'm looking at right now is two things. There's two things that I can look at. One, we see that 3 there, and we see a 2 and 2. So I know that there's going to be a 2 in front of that. I'm also looking at that, and I'm seeing that there's 2 iodines. So I can balance iodines by putting a 2 in front of the product side. So really any method you attack it will work. I mean, obviously check it in the end if you're unsure, but it's always going to work. So like I see that 3 on the right side. We can't put 2 into 3. So I'm just going to put a 2 in front. Now I just got to balance iodines and bromines. Iodines are already balanced because 1 times 1 is 2, and then I just got to put a 3 there. Hence we have bromines. 3 times 2 is 6. 2 times 3 is 6. And then 1 times 2 is 2. 2 times 1 is 2. So it balances out. So it's pretty simple. It's always like a matter of just low numbers. Don't plug and go. Like it's all right. So here we got carbon plus hydrogen gas diatomic from C2H6. Now balance everything but hydrogen and oxygens first. So I can put a 2 there. Now we got 2 carbons. Now we got balance hydrogens. We on the right side, on the product side, we got 6. And so a number doesn't always have to go in front of everything. And so we're going to put a 3 in front of that H2. And so now it balances out. Here, don't just put a 2 in front of the most complicated one. Although it would work, you would have to then divide them all by the lowest number. For example, let's say a student said, okay, well, that looks complicated. I'm going to put a 2 in front of it. They're not going to get it completely wrong, but they're not going to get it 100% right either. Like if they put a 2 there because they go, well, that always makes it easier. That's fine, but then it's going to be a 4 and a 6, and that does balance, but you then have to put in lowest terms. So it's going to be 2 carbon. So divide everything by 2 plus 3 hydrogen forms C2H6. So I assume that's the answer we got before. So don't put a 2 in front of that most complicated one until you need to, in a sense. All right, so I think we did this one also. We want to balance sodiums, and it's balanced. So don't think, put a 2 in front of that most complicated one. In a sense, maybe look for 3 down there if there's a 2 on this side. If there's a 2 on the left side or the reactant side, there's a 3 on the product side in the subscripts. That's when I look to put a 2 in front of the most complicated one. All right, so here's the last one. Now here, my brain automatically goes put a 2 in front of the most complicated one. But let's just see how it would work out if we didn't. So let's just try solving it like normal, balance the non-hydrogen and oxygens first, then balance. So now iron, Fe is balanced. So now balance the oxygens. I could put a 1.5 here and then multiply by everything by 2, but let's not do that just yet because you will have to do that, but let's do this first step. So now we can't balance it, with just normal numbers. So let's put a 2 in front of the complicated one and then balance it like normal. And there we go. Iron has 4. Oxygen has 6. And there you go. So like, you're not going to get anything worse than what we're seeing here. So if you can do these, try to do them all yourself as well.